as the thing is warming up, the projector, because the projector's on spring break too. Hope everybody's doing good. Good to see you guys. It's been like a month, a year, or something. Feels like it. Everyone have an okay spring break? Recharge? Good. Definitely needed. I had to stay the night in the airport. And that used to be fun when you're in your 20s, but when you're in your 30s, it's not. And that like knocked me out for like 4 days. So it was definitely like needed to have a little bit of a break. We're going to kind of ease into a new topic today. Going to be mainly conceptual, going over the next kind of second half of the content that we're talking about, which is going to be deep foundations and introduction to like pile design. Now, this whole class is, hopefully it's kind of been illustrated through this, like it's each one of these topics, like bearing capacity, like consolidation, all of these could be like their own class, basically, you know, like, so we're just kind of doing high level, skirt the surface. Here's like 2 or 3 methods to solve each thing. That's even more so for deep foundations. Like there are so many different types of piles, so many different types of designs, theories, all the things out there in the US, let alone like internationally. So keep that in mind as we are going through like the next 2 or 3 weeks on this topic. It's going to be very high level. We're going to be talking a lot about like specific generalized methods, but then still know that if you work in this field, especially if you work in like a specialty geotech area, you might be going into a deeper subject, you know, on deep foundations. So I wish I could have enough time to cover everything, but we're just going to keep it high level with that. And especially today, we're going to go overview of the generalized pile foundations. Now, because of that too, part of this class, I mean, it's in your syllabus and hopefully it's not the first time you've heard it, but we do have a group or a like term project. So the undergrads are going to be working in groups to work on a specific, like researching and teaching about one of these topics that we aren't covering on deep foundations. If you're in the grad version of this, then you're going to be doing it individually. So after we talk about deep foundations in the first half of this lecture, I'm going to go over the term project and the expectations, all that's on Canvas too, but we're going to go over that. And then also I'll go over the solutions for exam 1. And I'm so sorry. I usually try to get the exam 1 grades turned around much faster. But yeah, it's just been a slow like catch up for me. So I'm going to be working really hard on this week, providing feedback on that exam 1 on campus. Okay, well, let's look at where we're at. So yeah, we've switched a few things around before spring break. Today we are actually going to be starting our deep foundations, and as well as the exam 1 review. And then the next few weeks, deep foundations, it's all just going to be pile design. So we're going to be talking about estimating pile capacity, looking at drilled shafts capacity, and then also lateral capacity. And again, we're just talking about 1 or 2 methods to do that. And there's like 10 different methods, 10 different procedures. So we're only going to be scooting the surface. I'm going to talk about the ones that are important on like that they ask on the PE if you're doing the geotech PE. And then also like introduce some of the ones that are now leading and some of the procedures that are more on the research side to estimate the pile foundations. You'll see April 21st and April 23rd after exam 2. This is still on schedule here. For April 23rd, that's going to be our grad presentation day. So if you're in the graduate section of this group, then as I said, you're going to be working on your presentation individually. And then it's going to have a paper individually. It's going to have a required presentation. If you're in the undergraduate group, then you can do this grad presentation and you can present on your topic, but it'd be for extra credit. You just have to let me know so I can make sure we have enough time in the class to account for everybody. And this is before our project report is due, which is weird, but it's also the way a lot of actual submittals work in real life. So I just kept it that way, where you would present on it and then submit the final report afterwards. So yeah, keep in mind with the schedule, final stretch here. I know March was super busy. Hopefully April's a little bit more steady when it comes to stuff to do and just general absences, knock on wood. My kids have already been sick enough this year. Hopefully they have enough immune system built up to last me at least the rest of the semester. But yeah. Okay, so we're going to introduce deep foundations and specifically talk about the different types of piles that you might come across. In this class, we're going to be focusing more so on steel and concrete piles, but if you just look around, especially living on the coast or near the water, you probably notice a lot of different other types of piles, like wood and timber and composite and all the different sorts of things. So we're going to go over a very broad picture about what it means to design deep foundations and when we choose that. Then we'll go over the term project outline and then also your exam one solution. And again, the exam solution is generalized because there's lots of different procedures you could use. So I'm just going to go over like big picture what you should have done for each project. So let's recap a little bit. We were talking about the shallow foundations, and what were the two things we designed or we learned like to design for shallow foundations? Bearing capacity. Yeah. Bearing capacity is the shear failure due to a foundation. So we know that soil has some type of capacity or strength. And what we show that is as like a Q ultimate or Q. I don't know why we use a Q, but Q because it's in terms of like a stress. So it's a lowercase q, it's in terms of a stress or a pressure. And we know just from subsurface testing, we want to find the bearing capacity of the soil. Bearing capacity is going to be checked against the bearing load or the shear failure due to the foundation. And I talked about it in our class. The structure is going to apply some load that's fixed, a P, or sometimes it's shown as an uppercase Q, and this is a force. And we know that the stress is equal to, in this case, Q ultimate. This is equal to that force divided by the area. So oftentimes when we're talking about foundation design, we know the constraints of the soil. We know the capacity of this. We know the structural load coming from the weight of the structure, the live load, whatever. And it's our job then to solve for the area of the foundation that will safely transmit the structural load through the soil such that it does not exceed the capacity. So a lot of times, even though we didn't really do that in our design because it's an iterative technique, a lot of times we're solving for that area of the foundation. And then that's what we're recommending. Like this column needs to have an area of 5 by 5 or whatever it is, to transmit it in the soil. And obviously, as like a consultant in geotech, you want to save your client money and space. So you want to have the smallest possible footing size that you could use, because the larger the footing, the more prep work, the more concrete, the more all the things that makes it more expensive. Now, eventually, if you were to get to a point where this soil strength, like this, or these small footings, the area that's required, eventually you could get to a point where the soil is either so weak or the load is so large that this area required is massive and it doesn't make sense. What you might have like overlapped area or something. So what we're looking for again is that this Q ultimate, the capacity of the soil, is that greater than the structural load versus the area of the footing? And if the area of the footing is too large, maybe it doesn't even fit on the project, or the columns can't be spaced further apart enough, then what do? You can't use a shallow foundation. You have to go to a deep foundation technique. So shallow foundations most of the time are going to be the best bet forward because they're going to be the cheapest to install, the cheapest to maintain and design as well. You have less uncertainty when it comes to these shallow foundations. But if we have a case where you do the whole checks and you check your shallow foundation, sorry, you can't use it for whatever reason, the soil is too weak or the structural loads are too high, then you need to go to deep foundations. And then your mind goes to like, okay, well, which deep foundation? Because there's freaking dozens of them. And that's what we're going to be talking about today with that. So this is just on the bearing capacity side of things. The other thing we talked about too was settlement, right? That was the other kind of constraint. Not only just settlement as a whole, but differential settlement too. So those are the two checks that you have to do in shallow foundation design. And either one of those, if neither one of those checks work out, then you move to deep foundation. Because deep foundations usually, well, the settlement is occurring during construction, so you can account for it a little bit better. So yeah, you would go through either one of those. So let's talk about deep foundations then. So the different types of deep foundations are piles, drilled shafts, caissons, and sometimes like there's a bunch of other ones, but those are the ones we're going to be focusing on today. The whole thing is that with the mechanism, instead of, well, yeah. So the thing that like if you want to define these, instead of the so the force is transmitted vertically rather than horizontally. So with a shallow foundation, that structural load is transmitted horizontally in a footprint. And now what we need to think about is rather that structural load is now transmitted vertically through the soil. So the quote unquote area that our force is being transmitted across is through the length of the pile, like the sleeve of the pile, as well as the bearing cap of the pile, depending on the footprint of that. So it's only used when shallow foundations are not practical, whether it be settlement or bearing capacity, and like, or whether maybe the project doesn't have enough constraints, like, or doesn't have enough area, like for right of way and everything. So bridge foundations are often mainly going to be driven piles or board piles. Maybe you could also use these for ground improvement, like you see in this little photo here. Like maybe you just have a 10-foot layer of crappy soil on the surface, and you do the cost estimate as a consultant, say, okay, you can either remove and replace all this soil, or it's worth the extra money to do the driven piles, driven things for it. So some of the areas when you might have a recommendation for pile foundations, aside from the bearing capacity and the settlement, if you have weak ground conditions, then that might be one. So kind of in the cartoon we showed before, something that like organics or very loose or fat clay at the surface. And it might be worth removing it. It might not be, that would be one of the things. Yeah, each case is worth the investigation of it. The other time you might want to use these piles too is for large lateral loads. So if you think about it, like a pile essentially extends the center of gravity of the entire structure down. So like if we were talking about like some type of thing that has a lot of large lateral loads, like a overhead sign or a wind turbine or something that is very tall and slender, you want to lower that center of gravity such that it has less of a tipping moment. So for lateral, like piles can have a pretty significant lateral load resistance. We also have it for any like type of collapsible or even, I don't know if this is the right word, expansive. It just sounds like a weird way of saying expensive, but soils that expand, that would fall under the problematic soil at the surface. Again, like any type of swelling soil, you want to bypass that soil at the surface. That might be problematic and like reach and embed the foundation into a stable soil. Another one too that's often overlooked is if we need to resist uplift. And again, overhead signs, or I don't know, sometimes like Sometimes if you think about the what those big like towers that have the tension lines down and like the little footprints, like things like the transmission towers and stuff, you might need to resist uplift. And then of course, too, potential erosion is huge. So that's one of the main reasons why we use bridge footings and piles on bridges. Even if the bridge looks like it is on like a shallow foundation, that abutment or like the pier or something, you might see that cap, that pile cap, there's still going to be piles underneath it, just in case we have erosion and loss of that foundation under it. So and various factors of safety on that. So some of the other ways that piles are used that I didn't really learn about until I was working is also for temporary structures. So this is a photo from FDOT that have these H piles vibrated in. When I was working at a consulting firm, one of my jobs, I guess because I was like fresh and it was less of a severity thing, but I was working on these temporary wall foundations and I just thought that was weird. I'm like, wait, so we're doing all this design to just build something that will last a month and then you pull it out? And they're like, yeah, basically. So I was like, all right, well, low risk at least. But you're designing these piles. These are called soldier pile walls. You've probably seen them. They're normally stacked with wood in between each thing, and they're actually a retaining structure. And they use them as a temporary, like if they need to move traffic over to one side and build a temporary embankment. And since they're vibrated in, they can be vibrated out, and they're very easily like switched back and forth. So not only might you be designing like permanent foundations, you can also use this to design temporary foundations. And obviously the type of foundation, whether it be a H pile, like a steel H pile, would be more suited for one or the other. You can see right behind them, there's some bridge piers. It might be hard to see. This is like a bridge pier right here. That is going to be on a permanent foundation underneath it. Same with right here too. So yeah, temporary or permanent structures. If you were to just Google piles too, and I mean, you guys have driven around in Jacksonville, it's full of these too. You've noticed probably there's a bunch of different types, right? And like that's what we're going to be going over, the big picture of when the benefit is of using a concrete pile like this, a precast concrete pile, or maybe a timber pile, or maybe a steel pipe pile, or a grouping of H piles, and the different methods of driving them versus vibrating them versus like boring them and all those different things. So there's like, that's why again, like geotechs have that consultant title, is because there's lots of options. Each site's going to be specific. And so the engineer needs to know, like, instead of following a set standard, they need to know about the site. They need to know about the client's capabilities. They're willing to take on risk, and like how to best design something for that specific case, or consult with the client in that case. So yeah, I want to show this little video for FDOT that kind of illustrated a little bit about the driving. If you live out in Clay County or near First Coast Expressway, then you've probably heard and seen all this stuff. But if not, then this kind of overviews some of the pile driving techniques and just gives a good kind of discussion about it.
If you live anywhere near the I-4 Ultimate Construction Project, you've probably heard these sounds. It's the sound of pile driving. But what is pile driving for? And is it going to damage nearby property? Concrete, steel, and sheet piles are an essential part of the underground structures needed to create the foundations that support the new road.
Sorry, we just do this. It's dangerous. YouTube, oh no.
Check this out. I'm going to show you how I afforded this car.
Don't listen to this lady, it's a scam. No, don't listen to her. All right.
For Ultimate Construction Project. It's the sound of pile driving. But what is pile driving for? Is it going to damage nearby property? Concrete, steel, and sheet piles are an essential part of the underground structures needed to create the foundations that support roads, bridges, and ramps that will become I-4 Ultimate. About 7,000 piles will be driven into the soil along the 2100 project. There are two types of pile driving, vibratory and impact pile driving. Vibratory pile driving is used when the soil is soft and loose. As the pile vibrates, it gradually pushes the soil down. Vibration made by vibratory pile driving is high frequency and low energy. It's kind of like hitting a boxer's speed bag. If you're hitting it really fast, the impact is relatively low. Impact hammer pile driving, on the other hand, is more like hitting a punch bag like this. High impact and low energy vibrations are emitted from this type of impact. Hammer pile driving is used to make sure the pile is seated into the soil. All the I-4 Ultimate Corridor engineers carefully monitor levels of vibration in order to mitigate disturbances and to make sure the piles are placed accurately. Of course, you're going to hear it and feel it, but rest assured, we are monitoring to reduce the risk of structural damage. As an example, it was necessary to drive piles less than 25 feet from this historic property on Colonial Drive to Garland Avenue. During the entire process, structural damage occurred. And don't worry about the sounds of pile driving keeping you up at night. As part of the construction contract, driving is only permitted hours of 7 a.m. to 10 p.m. in residential areas. To find out more about pile driving and the entire I-4 Ultimate project, log on to I4Ultimate.com. Driving is only permitted between the hours of 7 a.m. to 10 p.m. in residential.
I think that's hilarious. So, they just like sneak that in there. Like, don't worry, we'll stop at 10 p.m. Like, your kids will be fine. They'll get 4 hours of sleep. But, all right. So in this video, this is just one project, obviously, but they used a lot of types of piles. Did you guys notice or pick on up on any observations like during this video of like the types of piles used and where? You guys see anything that like stuck out or any trends with it? So what types of piles did you guys see? Concrete. Yeah, concrete, and what else? Like right here. Steel pipe. Yeah, steel pipe piles. You know, hopefully like as you were going through some of the things, maybe some like stuck out to you where like, okay, like this right here, like what are we, these are precast concrete piles. And what are they being driven through? Yeah, through dirt, just through the ground right here. Does anyone know what these numbers actually mean, actually? Anyone seen these things? Yeah, so that's the depth of pile beneath it. So it's kind of fun when you're like looking at some of these steel pipe piles that are spliced together, and we'll talk about the whole splicing thing, but you can get an estimate. Like some of them for I-4 when they were under construction, there was one picture, where was it? You could kind of see, you know, some of the piles extended and were spliced upwards of like 280 feet. You know, you'd be driving next to it, you'd see 200, like not 80, 300. That means there's 300 feet of pile underneath that point. So in this, and this project's very specific with the contractor SGL and like what they wanted to do and everything, but hopefully you saw some of the trends where a lot of these steel pipe piles were driven in like marshy or through the lakes or something. And then a lot of the concrete piles were driven through sand and through dense areas. So we'll talk about that, but the mechanism of friction, like the general rule of thumb is like if you have a nice smooth surface, then you want that to be in contact with finer grained soil because you're going to be taking advantage of that cohesion a little bit more. Now, lakes and just clay areas like swamps and stuff, that's finer grained soil. So typically you would see these steel pipes being installed through those lakes or through swampy areas where like concrete being more rough on the outside, you want that to be in contact with granule or sand soil here. This picture too, good freeze frame. You can see with the pipe piles, these are a lot more or these are better in areas where you need to splice and you know you're going to have those extended lengths. And we'll talk about this when we go through each one. You can see them right there. They're actually welding. There's like these machines that just they put on it and they just do a weld across the entire pipe. And then you extend it much more easily than if you had a concrete pile where you actually have to splice it by pouring more concrete and waiting for hardening and all that stuff. So if you know you're going to achieve significant depths, then the steel pipe piles might be the way to go for that. And yeah, some of those, again, you can kind of see the number. I think this says 354 on some ends. Like there were really, really deep pipe piles, especially over Lake Ivanhoe, just north of downtown, because that lake is just deep with organics and like it was formed by a bunch of old sinkholes and all that stuff. So overview of each one. So go back. So when it comes to materials, there's timber or wood, there's concrete, there's steel, and then there's composite. Nowadays, most of them are going, like most geotech are going to be concrete and steel, like, you know, structural foundations are going to be concrete and steel. Now, concrete can either be precast concrete or it can be bored concrete, meaning like, or like they drill a hole and then they fill that with concrete. So there's two types. There's bored or driven concrete. So if it's driven, it's a precast slab of concrete that is driven into the ground, or there's auger cast, which means they're drilling into the ground and then when they're pulling up, they're filling the hole with concrete. We'll go over that in a little bit. Steel, it's obviously all going to be precast stuff, either H or, you know, square or different types of shapes, whatever we want. So the different shapes, the main ones are going to be our square piles, our circular, or what we call pipe piles. And then there's also the H pile for steel, which looks like a W or an I-beam, but it's more of like a geometric H shape for like a precast or a pre-thing of steel. For the construction method, again, it's either the cast in place for concrete only, or precast or prefab. Which can be used for steel and concrete for both one. So that's one of the things you need to consider. Like, is it achievable to transport these 60-foot long precast piles to our job site? Or is it easier and cheaper to just pour the concrete at the site and actually like do a cast in place method? And then the two main types of installation, we have displacement, meaning as we are installing the pile, it is displacing the soil or densifying the soil. So the other word for this is a driven pile. So there's no pre-drilling of a hole or anything. We're just hamming or pounding a nail into the ground, you know, essentially. Or there is a replacement, meaning we make some type of hole with an auger or a bucket or something. We dig some type of hole, we remove soil, and then we replace it with a pile. And so this is called our augering method, auger. Right now, if you fly out of JAX, they are doing some augering piles. They're installing a new parking garage as part of JX. So if you go and park and spend $14 a day to park that garage, you can see them doing these augering. There's a big boom and they're augering down and then they're refilling it with concrete. They're doing auger cast piles. One of the things we'll talk about. So overall, the whole goal of this is to transfer the load from structure into soil through 2 techniques. 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 2 through side friction. So that's this interaction of the soil and the side of the pile, and then also end bearing. So although it's much smaller, you know, compared to a footing, a shallow footing that might be 4 foot by 4 foot, that, you know, 24-inch surface area or whatever that end, that cap of the pile is, that's also has some resistance in some cases. So that's the two mechanisms that we'll go about. All right, so we'll talk about the most common type, I think is either steel or whatever, or concrete. But generally, when we're talking about steel piles, we're going to be talking about pipe piles, especially in Florida, or rolled steel H piles. Now, rolled steel H piles, that's what I was talking about before. These are very commonly used in temporary structures. And you vibrate them into the ground, and then you can vibrate them out of the ground. So some of the photos there seen here, obviously you can get really, really large steel like shapes, and these can be either driven or vibrated in. So this is one of the main differentiations between steel techniques and concrete piles. Is for concrete piles, you cannot vibrate them in like you saw in the little picture. Like instead of driving, you have the thing that just shakes the pile, loosens the soil, essentially liquefies the soil and allows it to just sink in under its own weight. And you can't do that with concrete because it'll break and chip and all the bad things. So a lot of times these H sections are preferred over some other type, like a W section or some other type of S section or I section over W, or I'm going to use the word beam because it's not a beam anymore, it's a column. And that's mainly because the thickness of the web for an H section is equal to the thickness of the flange. So these H's are nice and consistent, and they're easier to make because they don't have the fancy fillets and everything that you need for beams. So they're easier and cheaper to produce, and really you're just using them as like axial loading for the most part. And you optimize the friction in between with the shapes, with the geometry the way it is. So these can be extended through welding too. So extended depths through welding, which makes transportation a lot easier. Instead of getting an oversized load semi that is carrying like a 60-foot single precast concrete beam, maybe you guys have seen that on I-95 or something, you know, they have to shut down both lanes and you get the two drive trucks, and with the pilot trucks and everything. Instead, you can just stack a bunch of 40-foot sections on a single 55-foot semi or whatever, and then just extend them through welding. So the transportation is easier in that way. Also, then the pipe piles or whatever, they can be filled with concrete after. Which makes it a composite pile. So it's kind of a benefit of both sides, where you get the benefit of driving a pile, like an easily driven pile, and then you can fill it with concrete to increase the density of the pile or the lower the center of gravity or whatever you need. Maybe it's high axial capacity, so you need to have that really thick, like full or heavy dense pile to account for that. So you can kind of have the benefit of both worlds in there. So when it comes to applications of piles, a lot of times, as we said before, these are going to be used in fine-grained or organic soil. Now, you can use them in sandy soil and everything, but you have to be careful in larger grained soil, because if you have boulders or any significant things, these piles, and when you're driving them through it or vibrating through it, it's either going to knock it off course or you're going to damage the pile itself. So in areas of Florida where you have just like thick lake beds and everything with organic soils, that's fine. But in other areas where you have like glacial deposits, where you could just have a bunch of clay and then boom, a 20-foot thick boulder just randomly like underground, these piles would not as be applicable, because you're driving through nice stuff and then you hit that boulder and it breaks the pile and you just lost a bunch of money in a day's work. So the whole kind of mechanism of this is that the pile's smooth surface will stick to the clay and the silt. So you want to meet the fine grained soil with something that is more smooth, so you have that interface and you develop that adhesion for capacity. All right, that's supposed to move down in the arrow there. I wrote it a little small, but yeah, that's what that arrow was for. So the typical lengths, again, are pretty wide range. So like, I'm just going to say 10 to 60 meter. So like 30 to, I don't know, 200 feet typically, and all based off of transportation. But again, like we had upwards of 300 feet in Lake Ivanhoe in Orlando. Like, so you can splice them, you can add them together if you need to. So, but they can be small enough where you can still transport them on a single semi, which is nice. The typical loads, this really doesn't matter, but I have the spot here, so I'm going to put numbers here. So they can take anywhere from 670 to like 270,000 pounds or 270 kips. And it all, like, eventually you'll get into needing to do a structural design on the pile to make sure you're not buckling the pile under the load. If you have lateral loading, then you need to do like, basically cantilever or any type of beam capacity. So you have to consider those two when it comes to it. So the main considerations from a geotech standpoint is corrosive soils. So corrosion, obviously, since we have steel, if you have any pH less than 7, then they need to be protected or reconsidered. So you need to reconsider it. And obviously we use steel pipe piles a lot in swamps and in lakes where you might have some of those acidic conditions. So you have to account for that with corrosion. You have to ensure that they're treated and manufactured correctly, and you're not just buying steel from Ace Hardware to drive into the ground, because it'll eventually will corrode. The other thing too is deflection during installation. So if you have like some of these steel, like not the pipe piles, but if you're using sheet piles or if you're using anything thinner, as you're vibrating or as you're driving them in, like you can develop a significant amount of deflection. And that actually happened on the I-4 project when I was working on that. There was a few cases where you were, for whatever reason, like, rushed work, it wasn't set correctly, or maybe it hit something underground, but like some of the piles started bending significantly. And eventually when you get to a point, it's almost like a nail that you're hitting into the ground or hitting into like some dense wood. Eventually, you get to this point where it's like so bent, you're just like, oh crap, I can't use this nail. And you just lose it. You either hit the nail down, you can't pull the nail out. So you either like scrap the nail. And that actually had to happen. We had to scrap a few piles because they were too like bent and you couldn't get the capacity you needed out of them. So next time you drive over I-4, know there's like hidden piles on the ground and stuff. Yeah. So.
Do they ever like tree drill some of the driven piles just for like to help guide it down straight? Like tree drill just a little bit of the track out just so
yeah.
Go down a little bit easier. So
yeah.
Keep it on the track.
Yep. Yeah. For driven piles, yeah, like you would clear past utilities, so the backhoe would come in, like usually clear like the entire bent or whatever you're driving your piles in, not each one individually. But what you do have too is you have like a pile deck that essentially acts as a guide, so it's like 7 feet or 10 feet off the ground, and you're driving it from there. So you have 2 points with the ground. So that does help with it. There's another interesting case history. I couldn't find it, but when I took a class like this, there was an H pile that was being driven into the ground, and then literally it popped out of the ground like 30 feet away, just because it was able to have that radius, and it said it just like popped out of the ground when they were driving it. So you have to be cognizant of that stuff. Yeah.
I think that was bad.
Good. Yeah, there's different ways of testing it. Usually you know where the soil layers are underground, right, from testing. So you know, okay, at this depth we should like have some resistance, or we should have hit rock by now, or something. And so that's one of the ways. Other ways of it too is actually seismic testing on the pile. So like you stop driving and you hit the pile, and you actually have geophones or some types of sensors around the ground. And if you're getting pings over there, then you're like, oh crap, that pile's transporting that way. If you're super fancy, then you can put accelerometers on the piles, but then you're scrapping the accelerometer on the base, because it's buried underground. So like if you are in a really, if the client has a bunch of money and they want to insure it, then you could actually put some like sacrificial sensors underground and stuff for it. But yeah, that's one of the research areas to really test, because once the pile's underground, you can't see it, so that's a big thing. So yeah, this was one of the examples I just was going to show, like for it on downtown Orlando, is this little section here where they added on to the embankment, and then they installed, I think there was like 9 total bridges in this case, and there was buckling and or extreme pile deflection. So this is an example of that, where the cap actually gets messed up. You hit some layer that you weren't accounting for, or maybe you were driving it too hard or something, and then that pile can form like a plane, kind of like horizontal drilling. And then the negative thing happens, where that plane then shoves the pile in a different direction. And there was a few like pretty significant length pipe piles that were just buried, under like 400, 300 feet of soil in this area. And as long, like, the main important thing is like getting capacity on it. So it's important to, if scrap the pile, take the loss, as long as you still have something in that area that is going to have a significant amount of strength for the bridge. So you can see here that some of the pile caps that they were working on down there. Just looking on Google Maps, you can see those 3x3 spacing for each end bent. And you can see a little bit further down, what they do is when they install those pipe piles, then they install the pile cap that you see at the water, and then you put the bridge bent on top of that. So that's what's actually going on beneath the surface there. So overview with advantages for steel pipe piles. They're easy to handle and extend. The contractor doesn't need to be super careful maneuvering these things. They're not like concrete that if you like set them down on one side, they're gonna crack or something, or the loading on it, they're not extremely heavy because they can be hollow, and they're weldable, which is really nice. So different techniques to install. So you can use driven piles, you can drive them, and you can vibrate them in too. That's the benefit. Pretty adaptable geometry. So it's steel. I mean, as long as it's just different, you can get it in any shape that you want, or any cross section, or any lengths that you want. And they have very high load capacity. Especially in fine grained. And then also hollow pipes can be composite. So you get the benefit of that way. You install something that's hollow, then you can fill it with concrete or anything else within it. And then you have that composite material. So with disadvantages here, they're relatively costly. One of the most expensive types of it, just because steel is super expensive. So if you're driving the piles, and it's super loud and annoying. You'd think with concrete, you get a little bit more of a nicer thud. With driving steel pipe piles, that's the thing that like carries a little bit further. So that's the one where you have to account for it with like local businesses or whatever. You know, the concrete creates a little bit more of a vibration, like a discernible vibration, but the driving gets most complaints for steel. Corrosion is important to account for, and also the structural capacity of the pipe or of the pile. So they're a little less robust than concrete, where you have to, if you're driving a pipe pile, you have to ensure that you're not accidentally going to break the pile by deflecting it. So it could be like deflection, it could be buckling, all the things that we learned in mechanics of materials and in Dr. El Safdie's class. You have to account for that with our pipe piles and our steel piles too. So this is the area where, like, you know, a lot of times geotech and structurals are lumped together here for that. Like, is because yes, we designed the capacity for this, but we also have to account for the physical loading on the pile and not exceeding any of the capacities of the structure itself, let alone the soil structure interaction around it. Okay, so for concrete piles, generally these are going to be precast or cast in place. All right, cast. Or board piles. So these are where you could have a weird geometry or something where you're augering down and then you're boring it for it. So with these piles, they must be driven, or if they're driven, you know, they can't be vibrated in, they must be driven. So the benefit of this is that they can be reinforced if they are cast in place. And most of them are going to be like post-tensioned piles too. So you get that added structural capacity that you might not get with steel by having some of these cast in place or reinforced projects. So that's what you see here. These are board piles where they would pour the concrete or dig the hole, pour the concrete, and then drop the cage in of reinforcement. If they're precast soil, then they can be pre-tensioned or post-tensioned, that sort of thing. They can be extended through their extended length through splicing. It's not as easy as putting a machine on it and just welding it in like 30 seconds. Difficult. So yeah, a little bit harder to extend these. So these would be used primarily when you're pretty certain this length is going to be okay. So in variable soil conditions, then this might not be the best case scenario. Most of them have a simple geometry. Like a square or round or octagonal, any of the pictures there too. But also with concrete piles, you can also have I'm going to just call random geometry. So if you're casting in place, if you are drilling a hole and then you're filling that hole up with concrete, then you get the benefit of having a non-consistent geometry. You're essentially like filling the hole, meaning your hole might have the jagged, it might have like different lengths and everything, or that might have different diameters. So you get that benefit by filling the entire space. So that can add in like friction resistance of your pile. So that's one of the benefits of it. So for applications compared to our steel, mainly it's going to be coarse grain soil. So our sand or gravel. So the whole thing is surface of pile is rough. So what it does is it grips the sand, and the friction is a lot higher in these. So the typical length of this is kind of basically the same as before. Mainly going to be 30 to 40 foot individually max. But I mean, you've driven on the highway at like 2 a.m. You've probably seen those massive trucks taking them. You can get like the 80 to 100 foot length piles. You just have to get a specialized transportation on it for precast. Oddly enough, though, the record, I know everybody cares about Florida's deepest pile, right? That's what you guys are really on your mind here. The record for the deepest pile is about 410 feet in length, and it is a precast piles. They just spliced it a bunch of times. It was in like the 90s when they had nothing better to do, I guess. So, and that's over in like Lake Maitland or something. I don't remember the road exactly. It happened a long time ago, but apparently that's the deepest pile that, you know, like 410 foot in length. So you just have to splice it a bunch and it's a pain. Typical loads is, I'm just going to say, usually it's higher than the steel piles, simply because a lot of times the steel piles will have like the driving considerations, where these steel piles will be, you can't drive them as far because they might bend or break the steel, where concrete, you know, you can hit it with a hammer and just keep pounding it and get the higher capacities. Some of the considerations with this is the weight of the pile is actually important. These are heavy steel or pieces of concrete. So what the concrete, if you extend the pile too much, what you actually get is what we call a down drag. And this is a whole thing where if you work in geotech and especially DOT projects, they make you count this, the negative friction or the down drag, where the weight of the pile is actually so much that it mobilizes the soil and actually induce settling just because of the weight of it. So like that's one of the things you have to consider with some of these larger concrete piles. And then also the driving requirements. So we're gonna have like one slide about the different types of driving, like hammers and stuff. Most of them nowadays are gonna be double action diesel hammers, meaning like it's actually a motor that's like it's not just picking something up and dropping it. It's like an engine where you're like on the upstroke, you have an ignition and it pushes it down, and it's like essentially like a single stroke diesel engine. It's pretty nuts. But that is going to be required to drive these, where for steel, you might be able to use some of the old like traditional techniques because the resistance is not as high. So the driving requirement's pretty high for that. Okay, some of these here more economically, so it's a cheaper pile because it's concrete, mass produced, you know. Most of the time, the exact length is easy to produce. And this is because you can do a cast in place. So literally you just dig the hole and you pour the pile. So that's a board pile in that case. Generally, concrete lasts longer in the wilderness than steel does. So it's stronger and resilient, like especially underground, like you're gonna have less corrosion. Higher max capacity, because again, the concrete is easier to drive, or it can withstand more driving force. And then also the lateral capacity is usually higher for this too, again, because you can get them like they're heavier and lowering that center of gravity for it. The disadvantages is they can only be driven, can't be vibrated in. So you have to account for that. You have to make sure you have enough clearance and you've let the community know and you're not driving past 10 p.m., I guess. The splicing for extension is a pain. And also the transportation is a big thing for it. Again, the larger piles, you're going to have to account for that. You might have to do some lane closures. You're going to have to store it off-site or on-site or off-site if they're super long. So it can be a pain in that sense. All right, the last few we're going to go through quickly just because we don't have too much details on it, but these are still used. Boardwalks and everything, timber piles are used also in like ground improvement. So these are just generally the cheapest, most like private work. You're not going to use these for like DOT or any like large federal projects. They're classified into 3 categories. Good thing with these is they can be driven. They can also be pushed, which is nice. So you can sharpen it and you can actually just get a hydraulic push, like a counterweight for some of these lower capacities and just like hydraulically push them into the soil. They're not going to be super, super long. They're mainly used in like coastal or marine or like, like small structure settings. The boardwalks that they just installed like on campus, those are all through like driven wooden piles like this, or pushed wooden piles. So class A is what they call heavy loads. This is minimum diameter of 14 inches. So these are mainly going to be, guess I should add this too. You can also have them bored. Class B is medium loads, so diameter 12 to 13 inch. And then class C is for temporary construction work. So you can still use this if you need some type of retaining area or something. One of the weird things that we actually encountered for I-4 is there was a section in Polk County when they were constructing I-4, and I guess it went over an existing like old city line or something, that they had no idea, but when they were like demolishing and digging into it, you actually found a bunch of wooden piles that they used for the roadway embankment, and it was like lost to history. It was like must have been in like the 50s or something that they installed them. And so when they came to the site and they started, excavating, they hit stuff that looked exactly like that. The benefit of timber piles is that if you use native wood, if you're using cypress or something that's used to being that area, then it's not going to degrade. So like these piles were, underwater for like 50, 60, 80 years, and they were still perfectly fine, so they were kind of a pain to get up. So that's one of the benefits of it. Obviously, though, it's limited by driving because the wood will shatter or broom. So, usually you'll have shallower piles and then extend them through like splicing with metal sleeves. I'm sure we can all like think about that. There's like some type of metal sheathing around it, and then you just drill it in, and then that kind of acts it as a continuous thing. Again, most of the time it's going to be low structural load or lots of piles. Like, so you disperse. If you do have large structural loads, you have, sorry, it's like plies, wrapper piles. If you do have a lot of structural loads like this, then you would just have them close together and almost serve as micro piles. All right, applications. Boardwalks, jetties, especially in aggressive soil conditions. Anything temporary too, you might use this. So examples might be like heavily saturated or even underwater, like saturated conditions, organic, marine. And again, it's the cheapest of them all. So that's why I want to include this in here. If you're working on a project for like a private client or something, then like this might be a good option for like low structural loading. Although like DOT and federal stuff, federal highway, they don't even have standards for timber piles, is still an option to achieve the goal, like in consulting. And also very long life if you use the right wood. So if you're using it in the right conditions, then it'll last super long. So obviously the, low load capacity, only really shallow depths. So if you need to use this to like bypass like a 30-foot layer of nasty soil, you probably can't use it because it's not long enough. And also kind of the same as the inverse has long life in the right conditions. If it's wrong wood or wrong timber type, then it won't last long. So you got to make sure you choose the correct type of wood. So I think that's it with timber piles. So again, timber piles is still something that I wasn't asked on that PE, but it's an area that they're starting to look back on a lot more. Concrete and steel, those are going to be the most types of things. And that's the whole thing. You could teach a whole class on concrete. You could teach a whole class on steel piles. What we're going to talk about next class, we're going to start talking about the loading mechanism. And it's tricky because again, you have to keep track of the units for this. I'm using uppercase for the ultimate because now we're looking at capacity of piles in terms of a force. For shallow foundations, you look at capacity of the shallow foundation in terms of a stress because it's a force divided by an area. But now with piles, we look at it in terms of just a singular force because it's a point that's being distributed. So what we see is that this ultimate capacity is a combination of two things, the point bearing and then also the skin friction. But the tricky thing about this, I'm just teeing up for right now, one of them is going to occur before the other. So to mobilize skin friction, you have to have movement. Friction is only friction if something is moving against it. So that's the tricky thing in design is you actually have to induce settlement. And that's why driving it is beneficial because you're essentially driving it and you're mobilizing it over board piles where you might have that initial seating and that initial deflection there. Okay, so don't worry about these things because we haven't talked about them yet. What I want to introduce now with this before I stop the recording and we have 10 minutes, I'll just go over the exam stuff. This is now on Canvas. Your project tab there, you can click on that. You can go into people. What I've done, we've randomly assigned groups. If you have any issues with the group, let me know. We can switch stuff around. But what I want, the purpose of this is to research and to present in form of a 5 to 10 paper or 5 to 10 page research paper, any topic, whether it be any of these types of foundation designs that we're not going off of, that we don't have time to talk about. So any of them listed there, or any case history. So if you want to do learn about the foundation design for the Burj Khalifa or Brooklyn Bridge or Sears Tower, or any of the things that might be currently working or problematic, the foundations of subway tunnels and stuff, any of those can be, or you guys can use. So part of it is a research report. So it's going to be 5 to 10 pages, double spaced, where you're going over the introduction, history, governing design codes, or any of the design techniques. And then also potential issues with the foundation type and then specific examples too. So this is group project again. So I think it's 4 people per group. Some of them might have 5. But divide it up just like a lab report kind of from the old days and then work on it that way. With the presentation for the graduate group, it is required. For the undergraduate group, if you want to present, it is going to be extra credit. Now, for the undergraduate group, it's an individual presentation still. That meaning if everybody in your group wants to do it and work on this presentation, then you guys can just group present. But if only 2 or 3 or one person in the group wants to do it, then you have to present individually. And that's just to be fair for everybody. So you can't just tag along the extra credit if you can actually work on the presentation side. So there's more details on that in Canvas. What I want to go over right now is the groups. I think this is right, but you can also check. The topics are going to be first come, first serve. So I want to at least post on this. So there will be a discussion group, or you can come talk to me. If you want to do auger cast piles, then once you do that, then the group has it, and nobody else can work on that. That's just so we can learn from this report and learn from these presentations as a group, and we don't just have a bunch of repeat stuff. So again, the graduates are all working by themselves. I think I got everybody correctly. And then these are the groups that just the AI on Canvas created when I asked them to make 4 groups. So if there's any issues with that, let me know. I can switch stuff around. But I will fill this in and I will post this on a discussion group and then like fill it in as these topics get taken. So they're not like we're not double dipping into everything. So any questions on the random assignment of this? Again, there more details in the deliverable of it there if you guys want to look it up. But okay, well, let me know what topic you want. Let's go over really quickly some of the exam review stuff the next 5 minutes, and I'll start next class with this too if we don't finish it. So I'll at least try to get over the next one. Sorry for those watching online.